All right, we are ready for our next capstone presentation. This time we have Kaioke today, who will be speaking on what the Pfaff.
Hi everyone, my name is Kaioke and my capstone advisor is Dr. Jennifer Quinn. And today I'm going to be going over what the Pfaff. So I am talking about Pfaffians today. What the Pfaff is a Pfaffian. So a little background on Pfaffians. They're a function that can be performed on skew-symmetric matrices, and they were introduced in 1815 by Johann Friedrich Pfaff. What the Pfaff is a skew-symmetric matrix. So a matrix is skew-symmetric if the ij entry, that's the ith row and jth column, has the same magnitude but opposite sign as the jith entry, so the jth row and the ith column. So an example of a skew-symmetric matrix would be this. I've called this skew-symmetric matrix A. Notice that the main diagonal are all zeros. And if I pick a spot, so I'm going to choose entry 1, 3, so row 1, column 3, and I look there, and then I switch the places. So now I'm looking at row 3, column 1. It's going to have the same magnitude. They're both 2, but the opposite sign. This one is negative and that's positive. And so we have here -1, and down here's 1. Here we have 3. Here we have -3, and that's skew symmetry. So I mentioned earlier that Pfaffians are a function defined in skew-symmetric matrices. And what this means is you take a skew-symmetric matrix like RA, you plug it into the Pfaffian function, and it gives you a number. Here's what the Pfaffian function actually does. There's kind of a lot of stuff going on here, but the important thing to note, it is a summation. The Pfaffian function is the sum of a bunch of different things. What is the sum of specifically? Pfaffians are the sign sum over matchings. What the Pfaff is a matching. So a matching is a set of edges that do not share a common vertex, or that without common vertices. An example of a matching on 4 elements would be this right here. So we have 4 vertices, and notice that they share edges with one another, but no vertex has more than one edge that it's connected to. And the reason that I've laid this out like this, instead of having, a bunch of dots and then just kind of connecting them that way, is because by laying them out horizontally in a plane like this and then connecting them with these arcs that I'm going to call chords, it allows us to determine the sign of a matching, because matchings are signed. I mentioned earlier the Pfaffian is the sign sum over matchings. How do you find the sign of a matching? You take -1 and you put it to the power of the number of chord crossings in your matching. So for example, here, no, these chords do not cross, and so it's going to be -1 to the 0. The sign of this matching is 1. Okay. Some more examples of matchings. So on 4 elements, you could also have 1 go to 3 and then 2 go to 4. And in this case, we have 1 chord crossing. -1 to the 1 is -1. So the sign of this matching is -1. So if there are an odd number of chord crossings, it has a sign of -1. If there are an even number of chord crossings, it has a sign of 1. And then this is the last perfect matching for 4 elements. Perfect matchings are matchings where every single vertex is connected to an edge. And perfect matchings are the only ones we're going to worry about for the Pfaffian. The Pfaffian want their matchings to be perfect. So this is the last perfect matching on 4 elements. There are no chord crossings here, and so the sign of this is going to be 1. So how do you use these matchings to actually calculate the Pfaffian of a matrix? So let's take our first matching, the purple one. 1 goes to 2 and 3 goes to 4. So I'm going to look at entry 1, 2, row 1, column 2. I put a purple box around it so you know where the entry is. Then we're going to go to entry 3, 4, row 3, column 4. That's right here. You're going to multiply those entries together. So we have 1 times 1, and then you're going to multiply by the sign of the matching, which in this case is +1 because there's no chord crossings. And so the contribution of this matching to the Pfaffian is going to be 1 times 1 times 1 equal to 1. The second matching that I showed you, this one is having a chord from 1 to 3 and then 2 to 4. So I'm going to go to row 1, column 3, row 2, column 4. Multiply those entries. 2 times 3 is 6. 1 crossing, this is a sign of -1. So I'm going to do 6 times -1, and that is -6. And then finally, 1, 4. So I'm going to go to the 1, 4 spot. 2, 3, row 2, column 3. Multiply those together. This has a sign of 1, and so it's going to be 1 times -1 times 1 is -1. And so I mentioned earlier the Pfaffian is a summation. you have to add all these up and you get the Pfaffian. So we have the first matching contributed 1, the second contributed -6, the third contributed -1. Add them all up, you get -6. All right, so now we know, before we move on, actually, there is something to note. I said that the Pfaffians only care about the perfect matchings. If a skew-symmetric matrix has an odd number of rows and columns, the Pfaffian is 0. And the reason why is because you have an odd number of elements, one of them is going to be left out. You can't have a perfect matching on that. So for this presentation, you can do interesting things with skew-symmetric matrices and Pfaffians with an odd order. But for this presentation, we're going to focus only on the even order skew-symmetric matrices. So a skew-symmetric matrix that is 2n by 2n. All right, so now that we know what a Pfaffian is and where we can define it and how to calculate it, what do people use Pfaffians for? So since it has to do with matchings, you can imagine that it might have something to do with matching theory. It has applications in matching theory. It has applications in Aztec domino tiling, game theory, which is the application that the paper this capstone is based on was focused on, and also some areas of physics as well. So that's cool. We know kind of where they're defined, but they're still, or where they can be used, but they're still a little bit like strange to a lot of people. So it'd be nice if there's something that we could kind of connect it to that's more familiar. Maybe something that was introduced in matrix algebra and Calc 3, that'd be pretty cool. So Pfaffians and determinants. Arthur Cayley, you take an abstract algebra, you're very familiar with Arthur Cayley. He proved in 1849 that the determinant of a matrix is its Pfaffian squared. So if you take the Pfaffian of a matrix, you square it, you get the determinant. So let's go over a little bit of the intuition behind this. There's a lot of different ways to define determinants. The methods that you guys learned in matrix algebra and Calc 3, for example, I'm going to actually define the determinant, or I'm going to use a different definition of the determinant than what you're used to. So Pfaffians are the sum sign of matchings. You can think of determinants as the sum of sign permutations. What the Pfaff is a permutation. So a permutation is a bijection from a set onto itself. So let's say we have 4 elements. A bijection might send 1 to 2, 2 to 3, 3 to 4, 4 to 1. Notice that each element goes to something, and no 2 inputs share an output, right? If you've taken abstract algebra, you might recognize this as cyclic notation. I've written this permutation as 1 goes to 2, goes to 3, goes to 4, and then 4 goes back to 1. So that's called cycle notation. So here's how we would calculate the determinant using permutations. So that cycle took 1 to 2, so I'm going to go to the 1, 2 spot. 2 to 3, I'm going to go to the 2, 3 spot, 3 to 4, and then 4 to 1. You're going to multiply those entries, and much like the matching, determinants have signs. If you take an abstract algebra, you can think of the sign as the number of transposes that a permutation can be written as, -1 to the number of transposes. So this is actually an odd permutation. So you take 1 times 1 times 1 times 1, and then you multiply by -1. So this permutation would contribute -1 to the Pfaffian. Determinant, sorry. All right, so how do matchings and permutations relate? So I'm going to take 2 matchings, the purple and the blue one from earlier. I'm going to take one of them and flip it upside down, kind of paste it onto the bottom of the other. And I've actually just created a permutation. It's a little hard to see, but if you start at 1, and then you go clockwise from 1 to 2 to 3 to 4 to 1, this is actually that 1, 2, 3, 4 permutation that we looked at earlier. So there are 9 permutations of even length cycles that can be created this way. These are actually the only 9 that contribute to the determinant summation. Odd length cycle permutations are actually going to cancel out with one another. And if it's not a perfect matching, it's actually going to have a 0 from the main diagonal, and it's going to 0 out. So these 9 are the only ones that contribute to the determinant summation. There were 3 perfect matchings on 4 elements. 9 is 3 squared, so now I can maybe see a little bit of the intuition behind why the Pfaffian squared is the determinant. All right, so now we're going to look at some specific type of pattern matrices and see if we can figure out the Pfaffian of these types of matrices. The first one we're going to look at, I've called this one U. It's the, I call it the ones matrix because the upper triangular is all ones. The lower triangular is all -1s. It's skew symmetric. Main diagonal is all 0s because it's skew symmetric. What is the Pfaffian of this matrix? So in order to figure out what the Pfaffian of this matrix is, we have to look at the matchings on So I'm going to do it arbitrarily. So we're going to look at matchings on 2n elements. The examples I'm using are going to have specific numbers, just so I'm not like doing a bunch of dots to infinity. So let's look at an example of a matching here. 1 to 2, 3 to 7, 4 to 6, 5 to 9, and 8 to 10. This matching, every single matching, the magnitude of each of the entries is 1 because it's all ones in the upper triangular, which means that it's going to be 1 times 1 times 1 times 1 times 1 times the sign. So the only thing that actually matters for the Pfaffian summation is the sign. And in this case, there are 1, 2, 3 crossings. That's odd, so it's going to have a sign of -1. This is going to contribute -1 to the Pfaffian. It'd be nice if there's a way that we could kind of cancel out some of these terms of the summation, and that way we just end up with fewer things to deal with and count. Luckily, there is. So if you take the first chord of length 2 or greater, in this case, it's 3, 7, and you take the chord that immediately follows it, 4, 6 in this case, and you flip their endpoints, swap, so now it's 3, 6, and 4, 7, you have just created a crossing where there wasn't one before. Now there's 4 crossings, 3 here and 1 there. So this sign is now 1, and this contributes 1 to the Pfaffian. And you can go the other way as well. If you swap, take the first chord of length 2 or greater, take the next chord, swap it, you get that matching we had earlier. These two actually cancel out with one another. They contribute together 0 to the Pfaffian summation. Every single matching can cancel out with another except for the matching of consecutive chords, which has no chord of length 2 or greater, so no, you can't do that swapping. This has a sign of 1 because there are no chord crossings, and contributes 1 to the Pfaffian. Everything else cancels out. The Pfaffian of this is 1. So it doesn't matter if it's a 6 by 6 matrix or a million by million matrix, as long as it's even order and it follows this pattern, the Pfaffian is going to be 1. Therefore, the determinant is going to be 1. All right, so let's look at some more pattern matrices. What happens if we stick a 0 here? Since it's skew-symmetric, I also have to stick a 0 down there. What does the Pfaffian become? So remember that the Pfaffian summation is the sign times the entries of the matching, right? So there's the entries of the matching, there's the sign of the matching. And remember that I don't want to write that out all the time, so I'm just going to call this the weight of the matching, the sign and the entries, just the weight. So remember with our ones matrix, if you add up the weight of all those matchings, you got 1. Well, now we're putting a 0 in the ij entry, which means that we have to take away the contribution of all the matchings that contain the chord ij. Okay, so our Pfaffian is going to be 1 minus whatever the weight of all the matchings that contain, the sum of the weight of all the matchings that contain ij is. So let's say that my 0 chord is 3 to 7, all right? So this matching here contributes nothing to the Pfaffian because it's got 3, 7 in there, and I've decided to put a 0 in the 3, 7 spot. We can actually create a correspondence similar to the one we did before to figure out what the summation of the matchings that contain ij is. We can remove the chord. Now we have matchings on 8 elements. I've left the numbers the same so I don't lose my spot, but this is actually only 8 elements. The same exact correspondence we did before works. Everything cancels except for this. But when I put the chord back, I noticed that I didn't cancel out a 1. I've actually canceled out a -1 because there's 1 crossing here. And the reason there's 1 crossing, an odd number of crossings, is because 7, 3, 3, 7 is an odd length, even length chord actually. So 7 minus 3 is even. So when j minus I is even, the weight of the matchings that contain mij would have been -1, but we've zeroed that out, so we took that away from the Pfaffian. It turns the Pfaffian into 1 minus -1 is 2. If it's odd, so now I've gotten 4, 7 instead of, so that's an odd number. The difference is 3. Take it out, same thing. Everything cancels except for this, but when you put it back, it's part of an even number of matchings. And so we've actually just canceled out a 1, not a -1. And so we've got the Pfaffian is 1 minus 1 is 0. What the Pfaff does this look like? So if I've got a matrix whose upper triangle is all 1, skew-symmetric, if you decide to put a 0 here in one of these red spots, alternating diagonals, the Pfaffian becomes 0. And if you decide to put 1 in these alternating diagonals, the Pfaffian becomes 2. And that means the determinant is 4. If we add another 0, it gets a lot more complicated. We have to worry about the intersection of chords that contain the 2 0 chords, maybe. So I'm going to kind of skip that because it was a little complicated. I figured out it's either -1, 0, 1, 2, 3, or 4, depending on where you put the 2 zeros. And so you might imagine that if we decide to put 3 zeros, it's going to get a little complicated. And it's going to get more and more complicated. It's probably going to be like a, 16 values or something that's going to end up being. So we're going to be strategic about where we place our zeros. We're going to alternate them. So let's say we call this a checkerboard matrix. The main diagonal is all zeros, super diagonal is all ones, super is all zeros, super diagonal is all ones. So it alternates between ones and zeros. Skew symmetric, so down here we got negative ones instead. What is the Pfaffian of this matrix? So first thing to note, the 1, 2 spot is a 0, or the 1, 3 spot is a 0. In that case, the chord length is 2. 3 minus 1 is 2. So everywhere where the difference between the rows and the columns is even, there's a 0. So any matching that contains an even chord, we don't have to worry about at all. It's not going to contribute anything to the Pfaffian. We only care about matchings of only odd length chords. So an example is here. Notice that everything only has odd length chords. There's no even length chords. But if we try to do the correspondence that we did before, where we take the first chord of length 2 or greater and swap it with the next chord, it's actually going to make both chords even, and that's what we don't want. So in order to keep it odd, we're going to do a different correspondence. We're going to take the first chord of length 2 or greater. Then we're going to look for the next chord that's either nested within or crosses it, but we need to make sure that the first starting point of that chord is odd. So we're going to skip over 4, 7 because 4 is even. We're going to go to 5, 6 instead. Then we swap those endpoints, and we have created an odd number of matchings or crossings where there were an even number before. And so that flips the sign to -1, but we didn't make any even length chords, and therefore this still contributes. It doesn't contribute to 0. So all of those cancel out. So now the ones that don't cancel out are ones that look like this. So we have 1, 2, we have 3, 8, but notice that if we look at this first chord of length 2 or greater, the chords that are nested within, neither of them start with an odd number, so we can't do that cancellation. So all the chords like this have a sign of 1 because they have no chord crossings, which means that they're all going to contribute 1 to the Pfaffian. So if we want to figure out what the Pfaffian is, it's going to be 1 plus 1 plus 1 plus 1. We just need to count out how many of these types of matchings there are. So how do we count how many of these types of matchings there are? We're actually going to do it by looking at the power set. So the power set is the set of all subsets. If you have n elements, the power set is, so actually let's look at 4 elements. The power set is going to be the empty subset. It's going to have the subset that is the set itself, and it's going to have all the different combinations that you might have. So it's going to have each element individually as its own set, and then the combinations of 2, and then the combinations of 3, and there end up being 16 subsets of the set of 4 elements. And in fact, for n elements, the power set has 2 to the n elements. But for our counting, we're only going to look at half of these. We're going to look at the ones that have even order, so an even number of elements. Half of them have an even number of elements. 2n divided by 2 is 2 to the n minus 1. And we're going to draw a bijection between these matchings that don't cancel and the even order subsets of n elements. So if we have 2 n elements, they're going to be n pairs, and I've paired up the vertices. So 1, 2 is a pair, 3, 4 is a pair, 5, 6, and so on. And when we're drawing this bijection, we're going to look at the bridges, the chords that are greater than length 2 and bridge other consecutive chords. And you're going to find, so this is the first pair. This bridge starts on the second pair, and so we're going to say that this is associated with the element 2, and it ends on the 4th pair, so it's associated with element 4. So this matching, we can draw a mapping between this and the set 2, 4, which is an even order subset. And it turns out that it is a bijection when you do this. And so for a 2n by 2n skew symmetric checkerboard matrix S, the Pfaffian of S is actually just 2 to the n minus 1. And that means that the determinant is 2 to the n minus 1 squared, which is 2 to the 2n minus 1. All right, so we found the Pfaffian of a few different types of pattern matrices. Where do we go from here? So me, Jenny, and Jenny's co-author on the paper that inspired this Capstone project, Naomi Cameron, we're currently working on a paper with some of these new results. But we don't just want to like throw a bunch of like random calculations into a paper. We want to kind of have a story to tell. And so a couple directions that we could go, I kind of glossed over like what happens if we had 3 zeros, 4, because it gets really complicated. But one option is to try to follow that path and see if we can somehow connect adding zeros to the 2n to the checkerboard matrix. Another option, I mentioned that game theory was what the application that the paper of this capstone is based on was focused on. So we could try to find some applications to game theory for these pattern matrices that we found the Pfaffians for. That way we have a story to tell that isn't just, here's a bunch of Pfaffian calculations. So those are the two directions that we're currently looking at, and those are, what we might end up doing in the future, this spring quarter type of thing. All right, so I'd like to thank Dr. Jennifer Quinn for being my capstone advisor and helping me out with some of the tougher proofs for this project. Dr. Naomi Cameron, who co-authored the paper that this capstone was based on, and she also I've started working with her on this new paper that we are writing now. The UW Math Department has been very supportive and helpful, so I'd like to thank all of you. My parents are here, I'd like to thank them. And I'd like to thank Katie for always buying me coffees. All right, here are my references.
Okay, so one of the questions that you said you were gonna potentially ask was if you could just keep adding zeros.
Mm-hmm.
You guys have any idea like what it would look like if you reached the limit, I guess, or like reached like, oh, it's not working anymore, like breaking it, I guess? Would you know what that looks like?
Like breaking the like where it's to the point where you can't calculate a Pfaffian anymore? I'm not sure. I think that there's a lot of times where it looks like you can't calculate something, but there's just like a way you haven't thought of yet. So I'm not sure that there's necessarily a breaking point that we know of. I think Brooke has to be heading up.
When looking for a project, what kind of led you to this? Like, did you know anything about it before going into it?
Nope. So when we're doing the like 350, meeting with the advisors and deciding what you want to work on. Originally I was going to do flexagons because those seem really cool. They're like these little shapes you can fold and they do cool, I don't know, they do cool things. But then I thought Pfaffians sounded fun, the name. And then if you look at some of the things they can do, I didn't really understand it, but it kind of sounded cool to my not understanding brain. So I decided I wanted to focus on that. And Jenny also said that does have more like potential for, writing a paper and doing research in it than the flexagons did. So I ended up going that direction. Sav.
So you mentioned applying Pfaffians to like game theory,
Mm-hmm.
and I also remember that you did something like chip firing.
Mm-hmm.
Is that?
So the chip firing is something I did over the summer at an RU, completely unrelated to Pfaffians, no applications. It is a game, but it's not something that I'm sure you could probably end up doing something. And in fact, there were times in chip firing where I found matrices that were skew symmetric, and I was like, oh, does the Pfaffian have a relationship to things? And I didn't find any, but that might be a direction to explore, but it's not something that currently I'm seeing any connection between. I think Ronan, you had your hand up.
So what information like exactly does Pfaffian contain? Like let's say all the information you have about a matrix is it's Pfaffian. What would that tell you about the matrix?
I kind of depends on the context, I think, of what you're trying to do. I think, well, like for game theory, for example, if you look at an odd order skew symmetric matrix, so you know how like games you could like win or lose, so that's 1 or -1, you can actually make a skew symmetric matrix with that. And if you remove some of the rows and calculate the Pfaffians of the reduced matrices, then it can actually tell you some information about the strategy. I'm not sure, like generally, if you just have a Pfaffian, like what does it say about the matrix? I think it kind of depends on what you're trying to do or what the context is.
Okay.
Adam?
What was the range as far as each number in the matrix? Like how high could they go?
As high as you want. We did look at matrices that were not just 1s or 0s. We looked at ones that had x to the n for whatever x you want. And we were able to calculate the Pfaffian of those matrices. So there isn't really a limit to like.
Can you do this? Can you only do this with like a number line or a dots on a line, or can you do it with grids too?
Well, the way that I learned to do these proofs was by looking at the dots on a line. And for me, that's easier. But there are other ways you could look at the Pfaffian that might make it easier to look at. There's kind of a number of different ways, but the dots on a line are the one that worked best for me. Nee?
So are you going to continue to?
Yeah, I'm planning to continue to research them throughout spring and probably summer. We'll see. We'll see.
And are you going to practice grad school?
Maybe. I'm not really sure what I'm planning to do in grad school, but there's a lot of different directions I could go, so I'm not sure.
Okay, we should thank our speaker again.